The motivating dice example is spread throughout section 7.1, and we're looking at a test of goodness of fit in this problem. We're interested in finding out if a die is fair, so we've rolled 54 times and we're recording how many of each number we get. First of all, what would the null and alternative be for testing if the die is fair? So in doing a goodness of fit test, we're testing if different proportions match some specified values. When we're looking at a dice, we would expect every number to be equally likely or all be a probability of 1/6. So we're testing if our 6 proportions are all equal to 1/6 here. The numbers that we have in the null should add up to a total of 1, so we're counting for everything. So here, the P1 is the proportion of 1s, P2 proportion of 2s, etc. in the population. And then what we do for the alternative is write it out in words, and we just say at least 1 proportion in the null is incorrect. Then later in this problem, we look at actually calculating if the null was true and the die is fair, what would we expect to see for how many of the different numbers we should have. In this problem, we have rolled 54 times total. So we have a 54 for our sample size, and we know that we should have a 6 in each. So if we take our 54 and multiply by a 6th, we end up with 9 of each. What we're looking at then is how would we compare what we expect to have if the null is true, which is 9 for each, to what we actually had happen in our study, which was given on the previous page. And we're going to look at the difference in these, which are called our expected counts, and what actually happened in the study, which are denoted here as our observed counts, by looking at the observed count minus the expected count squared divided by the expected count. If they differ a lot and we get a large test statistic, then we're going to want to reject the null. If they do not differ much and we get a small test statistic, then we will fail to reject the null. For that reason, this is always considered a right-tailed test. Okay, so if we want to calculate this test statistic, that part is on another page here. So in 7.1.3, what are the test statistic and p-value for determining if the die is fair? Also check the conditions, and then what is our conclusion to finish off that example. So first of all, condition is that all e's are greater than or equal to 5, and they were all 9, so that checks out, so that's all we have to check. Our test stat is the sum of O minus E squared over E. So we had ones, there were actually 8 of them. We expected 9, so we do 8 minus 9 squared over 9. The next group for 2s, there were 7. Again, we expected 9. We expected 9 for all of them. Next one was 13. The next one was 11. And so these counts were given earlier as how many actually were rolled. The next one was actually a 9, so that term will go away. And then we had a 6. So if you find each of these terms and you add them all up, you get 3.778. So that's our test statistic. This has a chi-square distribution with degrees of freedom k minus 1. K is the number of categories. Our k here would be 6 since we had 6 different rolls for the dice. So we're looking at a chi-square distribution with a degrees of freedom of 5. So to get the p-value, we go look in StatKey. And at the bottom on theoretical distributions, you'll select chi-square. It'll prompt you to enter the degrees of freedom, so we enter 5. And then we're always doing right tail for these tests in Chapter 7, and then we put in our test stat at the bottom. And so it was 3.778. Hit OK, and we can see our p-value is 0.582. So with that p-value, we would fail to reject the null and say that we do not have significant evidence of an unfair die.